The water that flows from a city tap is not a fixed resource. It only looks that way. This assumption directly impacts critical systems. First, public health infrastructure. Second, urban agriculture and green spaces. Third, city economics, industry and consumer prices. It's an accelerated rewiring of a city's metabolic functions, not over centuries, but within a focused engineering effort. The first changes are subtle and technical, confined to the pipes and treatment plants. As the system matures, later consequences become far more visible and impactful. By the end, the world still functions, just differently. Most modern cities operate on a linear, once-through water model, a design born from a 19th century mindset of abundant resources and limitless disposal capacity. The journey begins far from the city limits, at a pristine source like a mountain reservoir or major river. From here, raw water is pumped long distances to a central treatment plant. There, it undergoes purification to remove sediment, bacteria, and other natural contaminants. That treated water is made safe for human consumption and sent into a vast, one-way distribution network beneath our streets. Once used, water becomes wastewater, laden with soaps, detergents, and human waste. It enters a separate network of sewer pipes, its value discarded. The environmental and economic costs of this linear legacy are immense. Constant withdrawal of freshwater puts strain on ecosystems, depleting rivers and lowering lake levels. Climate change and population growth are stress-testing those assumptions. The linear model offers little resilience. That vulnerability makes a closed-loop system, where waste becomes a resource, not just an environmental ideal, but an urgent question of urban survival. The first mechanical step involves rethinking the waste side of the equation. In our hypothetical city, the sewer network is repurposed into the primary artery of the new water supply chain. Every drop of water from every shower, toilet, and sink is no longer waste but influent, the raw material for the water recycling process. A major challenge is separating sanitary sewage from stormwater runoff, which can introduce unpredictable contaminants like oils, heavy metals, and pesticides. Once collected, the wastewater enters the heart of the system, the Advanced Water Purification Facility, or AWPF. This is a sophisticated, multi-stage factory. The process is a relentless gauntlet of purification, beginning with primary and secondary treatment to remove solids and organic matter. The water then embarks on the advanced treatment train, starting with microfiltration, where membranes block suspended solids, bacteria, and even some viruses. The next, and most crucial stage, is reverse osmosis. Here, extremely high pressure forces water through a membrane so fine that only individual water molecules can pass, removing dissolved salts, pharmaceuticals, and viruses. The final step is disinfection using advanced oxidation, typically a combination of ultraviolet light and an oxidant. This serves as a final failsafe, ensuring the resulting water is exceptionally pure. The newly purified water is a blank slate. It undergoes post-treatment conditioning, where minerals are added back to improve taste and protect pipes from corrosion. The city faces a critical choice. For our model committed to 100% reuse, direct potable reuse is the most logical path, pumping purified water directly into the main drinking water network. The network is under unprecedented scrutiny. A vast array of online sensors monitors parameters like pH and chlorine levels, feeding data to a central command center in real time. If an anomaly is detected, sections can be automatically isolated, containing issues before they ever reach the tap. The most immediate consequence is a shift to predictive management. The water utility is no longer a passive distributor, but an active manufacturer. This system is built on extreme redundancy. If a component has an issue, a secondary system ensures water quality is maintained while a crew is dispatched. The regulatory framework evolves. Public health agencies no longer rely on weekly sampling. Instead, they require direct access to the utility's real-time data stream. The city faces an equally formidable challenge: ensuring psychological acceptance. To overcome the yuck factor, a massive public education campaign is launched, rooted in radical transparency. Public taste tests are held, where blind tests often show most people prefer the taste and quality of the municipal supply. Despite this, a segment of the population remains skeptical, driving a boom for the bottled water industry and home filtration systems. The city counters not with bans, but with data. Over 1 to 2 years, with flawless operation, trust begins to solidify. Drinking recycled water becomes ordinary. The shift rewrites the utility's economics. Its single largest operational expense is now energy, creating a direct link between the price of water and the price of electricity. To manage this, the utility introduces time-of-use water pricing. This incentivizes residents and industries to shift high-consumption processes to off-peak hours. To ensure equity, the city implements a tiered lifeline rate structure, guaranteeing that water remains an affordable human right for all. Industries are incentivized to build their own on-site recycling loops, reducing the load on the central system and creating a decentralized network of efficiency. The most profound impact unfolds far beyond the city. By ceasing its large-scale withdrawals, the city gives its watershed a chance to heal. Rivers that were once depleted begin to flow more robustly. This restoration of natural flow has a cascading positive effect. Fish populations recover, and native vegetation flourishes, providing critical habitat for wildlife. However, this creates an unforeseen consequence. The ecosystem at the former wastewater discharge point, which had adapted to the constant flow, is suddenly shocked when the discharge vanishes. Years later, during a severe regional drought, the contrast is stark. While neighboring cities face rationing, our model city remains an island of stability. Businesses run without interruption, public spaces stay green, and residents have a reliable supply. The initial investment is proven to be an economic insurance policy. The city's vulnerability has shifted inward to the management of its complex, interdependent technological systems. The threat of drought is exchanged for the managed risks of a power failure or cyber attack. The ultimate outcome is a city that is more self-aware. It is a living testament to the possibility of decoupling urban growth from environmental degradation, a blueprint for a self-sufficient 21st century city. What scenario should we explore next? Share your ideas below. You've been watching IfVerse, where imagination meets possibility. See you in our next reality.